Hey, 8th graders, today's assignment is a gravity lab, and if you guys are watching this, obviously you guys are not in class today and are completing this from home. For your guys' assignment, your learning targets, I can collect data about the distance between objects and how this affects potential energy, and I can present evidence to answer the question of how acceleration due to gravity affects the rate at which objects of different masses fall. So for your bell ringer today, you guys have this system where we have a little ramp of books and a car on top of the ramp. So a student created a system that stores potential energy when the car is resting at the top of the ramp. What could the student change about the system to make it store more potential energy? So you guys should answer that right there. You guys also have this question here. The 4 balls on the left were all dropped from the height of 1 meter at the exact same time. Which one would hit the ground first? You guys should answer that and explain why as well. Okay, so for you guys at home, you will just be completing part 1. How I structured it in classes, I broke kids up into groups of 4, and 2 kids completed part 1. The other 2 kids in that group completed part 2, and then they came back together as a group and shared their results for each of their parts. So I'm going to obviously walk through what you guys need to do at home to complete part 1, and then I'm going to kind of explain to you guys the findings of part 2 so you're not losing information on that part as well. So make sure you guys watch through to the end of the video so you guys are coming out of this with both sides. Okay, so for your guys' part, you guys are going to be taking a look at potential energy based on distance above an object for a fall. So we're looking at gravity and potential energy. In this investigation, you will drop a marble from different distances above 4 layers of tissue paper to gather evidence about how the distance between objects affects the potential energy of a system. And what's really great about this experiment is also you get to tie in what you learned in the last unit on force and motion, especially looking at Newton's second law of motion where force equals mass times acceleration. And we know obviously our acceleration due to gravity is the same because we're going to be dropping this marble on Earth each time. But because we are putting more energy into the system or changing the amount of energy that we put into the system, we're also going to see it having a different amount of force of impact based on how high we're dropping this and the amount of energy that we're dropping. So that changes to an extent. The acceleration is the same, but the velocity then will change as it has longer to speed up or less time. Okay, so work with your group to complete these steps of the investigation. As a group, choose the 3 distances you will test. And this one, I think I did 20, 40, and 60. I think I even did a 4th one that had 80 in it. Okay, prepare 4 hoops with tissue papers, so 2 to 3 students. Stack the prepared hoops on top of one each other. Conduct the trial. For your first test, test the shortest distance your group chose. Hold the meter out upright with the 0 centimeter mark in line with the top hoop sheet of paper. Release the marble from the appropriate distance. Make sure not to add force to the marble. Measure the impact. And then observe how many layers of tissue paper were ripped by the marble and record the data in the table below. Share the data with your group members. Rotate reels and repeat. Your team should conduct at least 3 trials. If you have extra time and materials, conduct a 4th trial. So you guys should do 3 trials at 3 different heights for the video that you guys will be watching today to gather your evidence from home. You guys will see 4 trials there. Okay, so a distance above the paper. For this one, I did 20 centimeters, 40 centimeters, 60 centimeters, and 80 centimeters. So you'll need to record that. Okay, and then what you guys will get from this video here is the amount of ripped layers of tissue paper. So you'll right click that, open that link up, and it's going to take you guys into YouTube where you guys will be able to watch the short video that shows this experiment with me dropping the tissue paper.
Alrighty, good. So if you guys are absent today, you guys are going to
So it looks like that. So go ahead, use this to collect your data. Make sure you guys enter your data in there, and then you guys can pause this video while you do that and work through that. And then what you guys will do on slide 7 is you guys will graph that. So plot those 4 points, and then you guys will need to play a little game of connect the dots. So on the left, graph your data from slide 6 using a line graph. Use the draw tool to plot your lines first, then connect the dots with lines to finish your graph. Remember, if you hold shift while you draw your line with the draw tool, the lines will be straight. So you guys are going to start by looking at the distance above the paper. So if you recall, we did 20, 40, 60, and 80. So those will be your guys' 4 points that you're going up. And then you're going to look at the number of layers of tissue paper that were ripped through by the marble, okay, which is what you guys should have recorded on the last slide. Okay, then you guys will answer these questions. What patterns do you notice in this graph? And does this graph show us evidence of a cause and effect relationship? Explain. Okay, does this distance between objects affect the amount of potential energy in the system? So think about just in general what your total energy is in the system and how that relates to potential energy or stored energy. And then again, use evidence to support your explanation. Finally, how does Newton's second law, force equals mass times acceleration, tie into this concept of potential energy and gravity? So think about obviously what you guys are measuring is the number of tissue papers ripped, and that obviously takes force. A force that is exerted through a transfer of energy from potential to kinetic energy. So how does force kind of tie into that? Okay, and then finally your exit ticket for today. In a vacuum where essentially there is no air, which will hit the ground first, a bowling ball or a feather? Okay, and then once you guys have made that prediction on slide 11, you guys are going to watch this video right here on slide 12. Okay, so watch that video. It's pretty short. It shows this experiment in a vacuum and not in a vacuum, so in a normal atmosphere on Earth, and then which hit the ground first and why. Okay, so you guys will complete slides 1 through 12, but before you guys are done with this video today, I want to explain what the other side of the class is doing. So this is part 2, and what basically we're looking at here is dropping all of these. Okay, so based on what you guys saw with slides 1 through 12, if you've already finished those up, is that you might have some human error when you guys are measuring these, but for the most part, you drop these, they're going to hit the ball or the ground at the same time if we drop them at the same time. So what we did in class is we had each of these objects that we were able to drop, and we collected data on them, took their masses, and then we timed out using 3 trials and then an average the amount of time it took from the release of the tennis ball to it hitting the ground from a 2-meter distance. Same with golf ball, ping pong ball. An open sheet of copy paper, and then they wadded up the paper ball and turned it into a ball and dropped that as well. Okay, and what we find is that, there might be a little bit of difference in the times, but for the most part, they're all pretty close. So they should have answered the question, why did all the objects accelerate towards the ground? That would be due to gravity. Did any of these objects exert a force of gravity on Earth? Yes, anytime you guys have one force being exerted, there's also an equal and opposite force in the other direction. So when you guys did the PhET gravity and orbits the other day, you guys saw the 2 purple lines or the blue arrows that showed, all right, this is the arrow pulling the sun in from gravity, and then this is the arrow from the Earth on the gravity. So there's always an equal and opposite force, even if the Earth and the sun aren't in contact. Okay, so that's Newton's third law. Objects considered to be in the free fall are under the sole influence of gravity, meaning no air resistance. These objects fall at an acceleration of approximately 9.81 meters per second squared on planet Earth. This number does fluctuate slightly with changes in altitude. So as we go further up in altitude, we're actually going to see slightly less gravity, but not enough where you guys would float away or see a difference. Other planets have different acceleration of gravity numbers. Essentially, this number means that an object in free fall on Earth will travel downward 9.81 meters per second faster every second of its fall. Okay, so using that information and the average time for each of your objects, calculate the approximate velocity of your objects when they hit the ground if there had been no air resistance. So basically, you're going to take each of these times, and they were to calculate those by 9.81, which again, if we look at all of these times, they should be so close together that you guys really don't see much of a difference other than probably human error. Okay, what did you notice about your calculated velocity? Again, they all should be pretty dang close to each other. Why was there such a difference in time between the 4 types of ball and the sheet of paper? The difference being is when our sheet of paper is open, we have a lot more air resistance there. So we have a force acting upward, whereas the other balls have very minimal force acting upward against gravity. Okay, and then finally we look at this question here. What does Newton's second law have to do with this? So just like we looked at in your guys' part, we also have a component of Newton's second law here as well. Remember that force and mass are directly proportional. If you have one object that is 1,000 times more massive than a second object, you must apply a force that is 1,000 times stronger on the first object than the second one to get the same acceleration. So obviously, just like you guys saw again with the PhET gravity and orbits, when you guys looked at those blue arrows, we saw 2 equal forces but in opposite directions between the sun and Earth, even though those 2 aren't in contact. It's really no different here. So when we have a larger mass of an object, we have a gravitational force pulling it down, but we also have an opposite force that the Earth is going to feel as well from our gravity that matches by that mass. So remember, a more massive object has more gravity. So if we look at this elephant here falling, it's got a mass of 1,000 kilograms. So we're going to see a higher gravitational force, but we're also going to assume that it's going to fall at the same rate. So if we look at this and calculated acceleration based off this, because of the higher mass, we're going to need a higher force here. And those kind of cancel out to give us our 9.81 or 10 meters per second squared acceleration. If we look at this little dude that only has a 1 kilogram mass, okay, we need less force to pull him down. So there's going to be less force interaction between the Earth and this little guy and between that little guy on Earth. Okay, so it's just like looking at the moon's orbit versus the sun's orbit, okay, or smaller planets versus the Earth. They'd have, those smaller planets would have less of a gravitational force in between the sun and the planet. Okay, so you look at that and you say, all right, if we do the acceleration calculation for this little guy as well, because there's less force there, okay, there's also less mass. If we do the math on that, we come up with the same acceleration. So realistically, with no difference in air resistance, those two should fall at the same time. Okay, and then they had the same acceleration rate, or excuse me, exit ticket as you guys did. So that is it for your guys' assignment today. If you have any questions, please let me know. Remember that you guys are just completing slides 1 through 12. I hope you guys are having a good day, and I'll talk to you soon.